All right, so let's start the class. Now, first of all, let me go do one exercise from chapter 13.3. Okay. So this is a problem. It's maybe the homework problem. You already did it, and let me show you how to do it here. So it's going to be square root 2 t and e to the t, e to the negative t. Okay, I express in this form, and t is between 0 and 1. Find the length of the curve. Find the length of the curve whose vector equation is given by this. Okay, now you don't need to draw the curve. It's not necessary. Okay, and it just wastes of time. So all you have formula, the length of the curve is going to be integral from 0 to 1, length of the use. Okay. Now, you have to find the derivative next step. Okay, well, the infinite is been unstable. Okay, so you differentiate, it's going to be square root 2 e to the t negative e to the negative t. Okay, that's the derivative. Then your next step, you find the length. Okay, it is going to be square root 2 square and the e to the t square, e to the negative e to the. Okay. Now, if I randomly pick up vector function for the curve, I don't think we are able to evaluate the integral because it's radical involved. Okay, and but for this, for those problems, expert more likely again to evaluate the integral. Okay, so let's see what do we get. It's 2 plus e to the 2t, and here plus e to the negative 2t. Well, you have to do something, if possible, get rid of the radical. Then you can evaluate the integral, easily find the antiderivative, right? So for this problem, I think it's easy to do that. And that will be e to the t plus e to the negative t squared. Okay? When you square it, you get this. Okay? Now, I remember that SAT problem, you took SAT problem before. So it says that if, similar to that, if x plus 1 of x equals 3, what is the value of x squared plus 1 of x squared? Okay? So something like that. So you needed to square it, and then you find out x times 1 of x gives you 2. Twice of x. The product of those two terms is going to be 2. Okay. Similarly here, because e to the 2t, e to the negative 2t is just the opposite to each other. Okay. Okay. So then you can get rid of the radical. This looks great. Okay. So the length of the tangent vector is going to be this. Now, in some problems, you cannot get rid of radical, but you can still use a substitution to simplify the integral. Okay, so L is going to be integral from 0 to 1, and e to the t plus e to the negative t and dt. All right, right. Then you find the antiderivative for each of them. And the first one is e to the t, the second is e to the negative e to the negative t. And then evaluate at 2 endpoints, and you will get e1 minus to the negative 1 minus e to the 0 minus e to the negative 0. Okay, so the second part is 0. So what you get is e minus 1 over e. Okay, so that is answer. It must be positive number. This is integral of a positive function. So that is what I want to get. Okay, it took me some time to finish this computation. Right. Now, today's topic is about motion in space. And I already mentioned that before. So imagine, so given, let R to be our t, right? So, and t's start from A and B. So imagine this is a position function of a moving object. Okay, if you view it as this, yeah. So a position vector, okay, of a moving object. Okay, so that means that given this is origin at a given time t, and this point here, and this is moving in the space. Okay, maybe in that direction. So as I told you before, the derivative v equals v of t, which is defined to be the derivative of this vector function. Okay, and this is actually going to be it's called as a velocity. Yeah, the velocity vector or just velocity. Okay. Now, yeah, sometimes we say velocity vector. Okay, at the time t. Okay. Now, what's the velocity? And actually, the length. This length is called the speed. Right, this length is called speed. Okay, at time t. If the velocity vector is longer, then this length is longer, right? They're larger, so that speed is higher. Okay. Yeah. So why this is called the velocity? Think about it. Right. This is actually is this derivative, right? Is going to be limit as h approaches 0. Here's h r t plus h minus over t. So the difference of the two vectors, right? So that is going to be this piece. Okay, this is called the displacement vector between those 2 points. Okay. And this, of course, when h approaches, it's getting small. But if you divide it by h, then if it has a limit, then that is called the velocity. The reason is if you take the as a norm, this is going to be the limit of much easier to understand. Why this is called the speed? If you understand this is this limit, if we understand this limit, why this is called speed, then you understand the above limit is called the velocity. Okay, the norm of the difference. The norm of the difference of these two vectors is called the difference of the two vectors is a displacement vector, right, in a space. So the norm is going to be the length of those 2 points, the distance between those 2 points. The distance between those 2 points is divided by the time h, the change the time, right, and the limit. So this is going to be the average velocity. Then if you take the limit, then the average speed actually. Then you take the limit as h approaches 0, you get the instantaneous speed at that point. Okay, and if we remove the absolute value, it's not, but remove the 2 vertical bars, right? Then you get a vector, and that vector, yeah, it's reasonable. It's called the velocity. Right.
So the component, the r plus t plus h minus r of t over h is the average of it, average speed.
Yeah, this is easy to understand. This is the average speed. Because we look at those 2 points, the starting point and ending point, right? And in the space, those 2 points at time t and at the time t plus h. And you look at these two locations, right? Then you measure the distance between those 2 points, and that is the norm of the distance of those 2 vectors. So that distance divided by the time. This should be understood as a speed, right? Because the point moved from this moving object to another point. and how fast it is, you just take the, if you don't see the orbit, just in the space, there's a, you record the position of the moving object in the space at the time t, then you look at the position of this object at t times h, then you measure the distance. Okay, how to measure distance? Take the difference and take the norm. And that distance divided by the time change, right? This is a time change from t to t plus h. Then that should be speed. We don't call it average speed. That's the speed during that time. From one point, like a UFO, from one point to another point, go over there. So if you take the limit, then and that is the norm of the vector, R parameter. So if you remove the norm over that, then just the vector. So this vector we call this velocity. Okay. The velocity usually in the physics in high dimension, the three-dimensional space is a vector, not just a number. Speed is, that's small difference. Yeah. Velocity gives you more information than just speed. The direction, for example, right? Yeah. But speed is just a number, and it doesn't matter which direction you go. So now the velocity vector also changes in the space, right? It's not a constant vector. Sometimes it has constant length, and then this is this moving object has a constant speed. If it does not have a constant length, then this moving object does not have a constant speed. So the speed will change. When the speed changes, you get an acceleration, right? So so it's reasonable to call this vector. This is actually a double derivative, and the derivative of the velocity vector, which is a double derivative of the original, right? And this is called as the acceleration. Okay, or acceleration vector. So then you get, you get the second derivative, right? When you differentiate the position vector twice, you get the acceleration. All right. Now, we sometimes we want to recover the orbit. If I know if I record the velocity vector, okay, then can we figure out the orbit? I think it can be done, right? So in the space, if this is the starting point, okay, if you know that's done, and if you are given the information, this is R over T, okay? If you are given the information of the velocity vector, okay, you can get the position vector back. Okay, this is the first fundamental theorem of calculus, right? It says that the integral from from A, okay, from A to T, right? R prime tau d tau, I use another prime, otherwise it's the same thing. This is going to be R over T minus R over A, okay? So in other words, the integral of the velocity vector, I can change the notation, VLT, VL yeah. So if you're given the velocity vector function, and you integrate it, and it is a starting point, then you get the position of the moving object, right? So this just follows some calculus, the fundamental theorem of calculus. And similarly, since the acceleration is the derivative of the velocity, right? Velocity, derivative of velocity. So the same idea, you can get, the same idea you can get, you integrate both sides. Yeah, so velocity is going to be This is tau and a b. Okay, the integral of the acceleration, okay, plus the initial velocity, you can get the velocity at time t. Okay, so we have these two formulas. Yeah, this is why we needed to learn how, the integral of velocity vector function. All right, so those are the two formulas. Then let's take a look at some examples. Yeah, we're given position vector and moving object. We want to find the velocity, acceleration, and the speed. Okay, this is called the position vector. So that's going to be 1 and t and the t squared. Okay. So first of all, the velocity is going to be the derivative of the position vector. So it's going to be 0, 1, and 2t. And then the acceleration is the derivative of the velocity. And that's going to be 0, 0, and 2. And the surprise to me, in this case, the acceleration is a constant. So this moving object in a space speeding up and at a constant rate. Okay, even it does not change the direction of the acceleration, does not change the direction. Okay, it's independent time t. Okay. So let's then we see that the speed, the speed is going to be the absolute value of the velocity. Okay, so it's going to be 1 plus 0 squared plus 1 squared plus 2t squared, which is going to be it's 1 plus 4t squared. So clearly, the speed, as time passes, it's getting higher and higher. Right? Yeah, the speed. Okay. And then actually the direction also changes, right? The velocity, the direction changes. This is the direction which is the moving object moves, right? That's all we need to find out. Now then, sometimes we are not given the position vector. We are given some other information. For example, like a flying object in the space, right? You cannot constantly to get the position vector. What they did is that the equipment inside the object, right? Inside of this space, whatever you call it. So it records the acceleration and its direction. Okay, and can you recover can you draw the orbit in space? That's why we have to solve the inverse problem. And this is possible. You get all the information back on the Earth, and you see you get the acceleration vector. Then you just integrate it twice. You can get the position right, and you can tell where it is. That's amazing, right? Yeah. Sometimes you can only get information, just the velocity vector. Then you can figure out its orbit. Okay. So we know that it starts from this point, okay, and we are given the initial velocity. It is going to be 1, -1, and 1. Okay, and the acceleration, I got the information about acceleration is 4t, okay, and 6t and 1. I want to find out the position vector at the time t. Okay. So we already know that this is. I also know that the initial velocity is in that direction, and the object is flying going away. Okay, but I know the acceleration, the vector. okay, at the time t. So can I figure it out as an orbit? Okay, it's a position at any time t. Right, so we can do that. And how to do that? Step by step, right? We find the velocity vector first. So the velocity is going to be 0 plus integral from 0 to t and a and tau d tau. Okay, so that's the first. And here's a 4 tau and a 6 tau and a 1 d tau. And then you just integrate each component. Right, and the first antiderivative of the first component is 2 tau squared, and this will be 3 tau squared, and this is a tau, and integrate between 0 and t. Right. So you will get 2t squared, 3t squared, and a t. And when you plug 0 for tau, you get 0. So this, you can combine them into 1. Right. So this is a vector, this is a velocity vector. Yeah. Then,
Where did you get the bounds for the integration? You're just making the assumption that it's 0 to t because it's going to be moving.
yeah, it's the integral from, integral from 0 to t. That's why this means to take a difference, right?
Is that always the case?
Yeah, you see, if this is the integral of the derivative, right? And if you don't write it like this, then that's fine. You can just f up, right? Then the theorem says that if you find the antiderivative, right, and this will be this, the difference of the value of the antiderivative at the end point. This notation means f of b minus f of a. Okay.
No, Professor, she's not asking about how the process works. We're just asking how do you know it's from 0 to t? Why is it not from 0 to 1 or 1 to t?
No,
exactly.
We are asking to find the general formula for the position vector. So we do not specify the time. We just say, hey, arbitrary time t. So that's why this integral is from 0 to t. So this is how do you get to the,
so you're saying 0 to t just as an example or a formula, but it doesn't have to be 0 to t all the time. It could be
no, not
1 to
necessarily. If we are given the initial position at the time t equals 0, then this is a t 0 is always, yeah. If it's from t equals 1, then the integral is from 1, okay? Yeah, here you see, it's the initial position, initial velocity is at t equals 0, right? So that's why we have this formula. In my general formula here, I just say from a to t, right?
Gotcha, thank you.
Yeah, from a to t, because I do not specify the starting time. Okay, time could be 1, or could be 2, could be 0. Usually when we say initial velocity, it means the time equals 0, usually, okay? All right, so then the position vector is going to be the initial vector plus the integral of the velocity, okay? So that's the word, that is the formula, okay? Then I already get this formula, and what is R there? And it's going to be 1, 0, 0. And I'm going to put, assuming this computation is correct, this will be t squared minus 1, and tau plus 1, and b tau. And the reason I changed the tau is just because it looks like a t, but this should be different from the one end point of the integral, which is t, from 0 to t. Otherwise, confused. Yeah. Doesn't matter. You can change it to another variable inside the integral. Okay. So then you find the antiderivative of the first component. That'll be 2 over 3 tau cubed plus tau, right? And this will be just tau cubed because when differentiate gets rid of tau squared minus tau. And here is half of the tau squared plus tau. And still integrate. And take a difference at the turning point. And when you plug 0 for tau, it's always 0, so don't worry about that. We just need to replace tau by t. Okay. Now, on the quiz, for example, if you don't have enough time, just stop that. If we add them together, and you move to the next, move on to the next problem. Then you come back to add the two vectors together. You are not going to lose any points at this point. And it's clear. You got all the information. Okay. Now, Newton's second law of the motion says that if you see the object in space moving, right, it will not move automatically, okay, in the space without air. There's some either internal force or the or external force acting on that object. If there's no force acting on this object, then this object will not speed up, will not slow down. We fly at a constant speed, okay? And maybe the direction will be not changed. It's just a fixed direction, right? Yeah, kind of, yeah. So because the acceleration, there's no acceleration. But Newton find out, let me write down Newton's law. So this is an object. If there's a force acting on that, okay, then it will change if the force is a direction, it's a vector, okay? It has directions, the length of the force just tells the force, how strong the force. So this one acting on an object, the result is the velocity, the acceleration will be changed proportionate to the force. So the Newton's second law of the motion, it says that the force at time t is proportional to it's proportional. So let's use m. The constant is m, and proportional to the acceleration. Or the acceleration is proportional to the force acting on this object. Okay? Acting on this object. So if there's no force acting on this object, then the acceleration will be not changed. If the acceleration, acceleration will be 0, okay? Right? If acceleration is 0, then the velocity will be a constant vector. Now remember the velocity, right, is going to be VA plus AT and A tau d tau. So if there's no acceleration is 0, then the second part is 0, the integral, right? So the velocity is always equal to the initial velocity. So that means it's the object flying in space at constant rate. So that's why when we send a space shuttle, for example, some kind of, to the Mars, right? So at some point, it flies at a constant speed, okay? And at the very beginning, you have to speed up. So there's a force, internal force, push a lot, right? And the speed up at a certain point where you turn off all the engine, right? Turn off the files and it's fly at a constant speed. But somewhere, the gravity of another star, planet will also pull this orbit. It's not like absolutely, some space, empty space there. Okay, it's very complicated computation, actually. Okay. So then you have to control the, control the object, yeah, the spaceship. In some direction you maybe start a fire and push and change the orbit. This kind of things. It's not easy to do this. Okay. So this is a formula, and what we want to do is we are given sometimes we are given the force acting on basically acting on this object. Then we want to figure out how fast what the speed changes. Okay.
Are you talking about projectile motion? Is that what you're talking about?
That's right. Yeah, that's right. So we probably not get into too much detail about this physics part. We just need to know how to do the mathematics. We are given the acceleration. The constant is also given. Okay, we are given the acceleration, and that's what we did above, and trying to figure out the vectors, trying to figure out the vector velocity vector. Okay. What we want to study today is in mathematics, as you see that this is the orbit, right? It's moving up. Okay. If you get first of all you get the unit tangent vector. Okay, the unit tangent vector is going to be this the position derivative of position vector. You normalize it. Okay, then we would we know how to find the curvature. Then you get the normal vector. Okay, the normal vector. It's not easy to get a normal vector, okay, but I know there's normal vector. If it's parameterized by arc length, okay, then the normal vector, okay, if it's parameterized by arc length, it's called ds. Then this will be the curvature and the times normal vector. Okay, that's a formula, right? And the derivative of the tangent vector with respect to the arc length is going to be perpendicular to the tangent vector. Okay, it's perpendicular to the tangent vector. Okay, and this, if you normalize it, okay, if you normalize it, then you get unit vector perpendicular to t. Yes.
So we talked about the big T of t, the normalization as being the tangent, right? And then the normal vector. But when we're talking about this right here where it's k, we're talking about the curvature.
Yeah.
And does that mean that it's smoothing out the variabilities that a curve has? Like if you had data points, right? Or is it actually giving us a value of like how
no, the k, we find out, you see, if it's
k is in like 13.3, right?
Yeah, this is 13.3. I'll go back there. So this k is nothing, just as a derivative, the length of this derivative of the tangent vector with respect to the arc length, and that really tells you how curved this curve at that particular point. Okay, and if very flat, this could be almost equal to 0. Okay, and if it's like a circle, and the circle is getting smaller and smaller, and the curvature is actually increased. Okay, it's curved evenly because it's around the circle, but the curvature, okay, the circle is getting larger. Then if you look at this point, it's become more flat. Okay, that's why on the thinking about the Earth, for surface we can also talk about curvature, but on the Earth you are so tiny when you stay at the point, you find that the Earth is very flat. Okay, the curvature is almost equal to 0 of the Earth's surface. Okay, and if you stay on the circle, if the circle is huge, circle, then you only see a straight line, almost a straight line. So the curvature is almost equal, right? But the definition of the curvature and the normal vector is using the arc length, but it's not easy to get arc length, okay? Reparameterize that. So we just use the arbitrary, vector equation for the curve. So in that case, it's easy to get tangent vector, but it's not easy to get the normal vector, okay? And so there's a formula in section 13.3, and how do we find the normal vector, right? So the normal vector is going to be the cross product of the second derivative. So let me give you record the formula here. Yeah, this is a normal vector, yes, okay, cool.
Professor, I have a question regarding the in 13.3, we've got in the book that formula or rule number 10 or 9, 10, 11. And is that something we would be given that upon the question when we have an exam or a quiz?
Rule number, you mean the derivative, the rules for the derivative?
No, for the curvature.
Yeah.
The curvature.
Yes.
Well, the curvature formula, you have to memorize it. Okay?
9 through 11 plus the normal formula.
Yeah, we have you see, for the normal vector, okay? For the normal vector, yeah, there's a formula here for the normal vector. And the curvature formula, if you use the arbitrary, parameter, then the curvature formula is going to be the cross product. You have to complete this cross product, okay? You don't need to go through each step, just to find the first derivative, second derivative, then you take it the cross product and takes a norm and divide by r prime of t, and the norm of that is q. Okay, that is given in the book on page 907. Okay, but this is a quiz. Okay, you are open book quiz. You don't memorize it, it's fine. You just look at it, okay? Clear? Yeah, I'm not going to monitor. I cannot monitor. We were thinking about like turn on the camera. You can, I can watch. That's not allowed. So you then in that case you can take a look at the textbook when you do the homework. Do it on the quiz. Okay. Yeah, it will be. It should be very careful about the parameter. Okay, take a look at the normal vector, the binormal vector. Okay, and we got this formula. This is we got this formula. It's given in arbitrary parameter. Yeah, if t is arbitrary. Yeah, it's not necessarily, it's arc length, okay, just time t. So the normal vector here is going to be, it's given in the book. You just find the derivative of the tangent vector, then you have to normalize it. Okay. And so we have a normal vector, we have a tangent vector, right? At each point. Now, how do you find it? There's some formulas that you can find out. Then, now we go back to the moving object, okay? The moving object, and you can see that the velocity, okay, the velocity, you can, yeah, let's look at the first example, right? So the velocity vector, okay, is going to be just r prime t. So I can
you scroll up on your screen? There's like this black box at the bottom. Yeah, there we go. Thank you.
Yeah. So the velocity vector is going to be the derivative position vector. But according to my above formula, this is going to be, if you want to express it in terms of the tangent vector, will be some vector in the book they use a v. You know, it's easy to confuse with my velocity. Okay, but just a v. Okay, so this is a capital T. Okay, so actually this v, well, I don't think we should use the same v here, because in the book, you know, when you type it up, you put this bar here, but I don't want to, this arrow symbol. So it's see what kind of notation again. I'm going to use slightly different notation. So otherwise it'll be confusing. And the right. So I'm going to call lambda. Okay, lambda is going to be the length of this. It's actually the speed. Okay, this is the speed. Okay, and t is a unit tangent. You know? Okay, and I can put a t here. You know. Okay, so this is a t. Okay. Then the acceleration, okay, is a vector, and the acceleration is a second derivative of the position vector. Okay, and we can express it in terms of, see that let's use this formula, right? So I get the derivative of velocity, right? Then I differentiate this part. It's going to be lambda prime t, capital T, and the lambda t, capital prime T. Okay. Okay. We know that this one, okay, it's in the same, actually, this is a picture. This is a t, that's in the normal vector n. Okay, now where's the t prime? T prime is somewhere here. Okay, so it will be the same plane between t and the capital N. This is how do we, yeah, you know, this is a, so I can explain this a little bit later. But then, if you want to use another notation, okay, that's called the, a capital T plus a nt. Okay, so the velocity, the acceleration can be always expressed in terms of those two components, because the acceleration vector, what I'm trying to say in there, is in the plane spanned by n and t. Okay, the acceleration. So we want to find out the components on each of that vector. Okay, the components of t and the component of n. Okay, so this is called the tangential and the normal components of the acceleration. So our goal is trying to find the determinants two functions. Okay, if we want to put a t here, then it's a function t. Okay, so the question is, how do we find it? Okay. Yeah. So the normal vector is going to be, well, the same. I should say this is the same, yeah, from the definition. We already did, you see, look at the above, right? This is a capital prime T. Yeah, we normalize it. Okay. So so this is this is a picture. See, go back here. So this is a normal vector. Definition of normal vector. Right. Okay. And the tangent vector prime is going to be the derivative of tangent vector is perpendicular to the tangent vector. Okay, and you normalize it, you get to the normal vector. So now, so you are given this component. Okay, so I can tell that immediately because the difference between these two, right? The difference between those two is going to be first of all, you can see that this is so this n of t is going to be the norm, is the normalized tangent, the derivative tangent vector. Okay, so when compared to coefficients, a capital T is just a lambda prime t. Right?
Professor, and this is because we're talking about something being in motion, right?
Yeah.
So what we learned in physics was that there's often at least two components to motion, right? An up and a sideways. And so that's what we're doing here is we're breaking.
Yeah, we were trying to we're trying to express the acceleration as in terms of the tangent vector and the normal vector. Okay.
Which is the two different directions of motion.
Yeah, that's right. If then this is so this is in mathematics you can always find a moving frame around this orbit. Okay, so this is if we call it coordinate system, this is a B. So imagine if in the moving object around this orbit, then you have a coordinate system. Okay, we call it moving frame, moving around this curve, and maybe it's rotated. Okay, but there's one vector is not going to be changed, just the tangent vector. The tangent vector is always tangent to the orbit. Okay, then then n and b may be rotate, around this curve. It's possible. Okay, but we want to express the acceleration. Okay, acceleration in terms of t and n. Okay, because the velocity vector is always proportional to the unit tangent vector. So right now, we have this moving frame and have a t and b. Okay, so the velocity vector is going to be proportional to the tangent vector. That's how do we get a unit tangent vector. That's how to get a unit tangent vector. We just normalize it. Okay, so lambda t is going to be this. Okay, and based on our calculation, we can find this. Okay, and then you will see there's a difference between those two. The difference between this n is going to be, you can see n can be replaced by this part, then capital N, n, right? So I'm trying to find the formula here. So capital N T and divided by is going to be lambda t. Okay, compare both sides. So that implies but the point is, we have to do some computations here. So this is the formula, but the book tells you, and this is also equal to curvature times lambda TL squared. Okay, and that's if you remember how do we define the curvature? This is from the curvature formula can replace the curvature formula. Okay, so that is K. Yes, that's lambda. Yeah. Okay. So this is a two component, and we can calculate. So in order to calculate this two component, all you have to do is just find the length of you just find the speed. The speed is derivative gives you the first component called tangential component of the acceleration. Then if you have to find the curvature, curvature times lambda square, then you get this, right? So I just want to quickly discuss the examples in the book. So then we take a quiz, okay? So we are given the velocity, position vector, so t square, t square, and the t cube, okay? It's very arbitrary, okay? So what you do is you find the derivative, right? You get 2t, and 3t squared. Then you also find the second derivative, that's 2 and the 2 and the 6t, okay? And first thing you have to find out is the speed, right? I said 2d. So that is going to be the square of each component, okay? Then you simplify it. 4 plus 4 is going to be 8. And this will be 9t to the fourth power. Okay. Now, how do we find this tangential component? The tangential component is just a derivative. You can use this directly, find the derivative find the derivative of this lambda t. This is my lambda t, okay? You can also, let's find this, okay? So the next part is slightly different from the book, because in the book, it also gives you the formula. You can figure out why this is true. You have to, the dot product actually, okay? There's several formula there. Yeah, it is better to derive it and, to figure it out. I do not want to give you another formula, okay? So what I'm going to do is I just compute the derivative directly, okay? So I get this. This is my lambda, okay? And this is my lambda t, okay? The derivative of lambda is going to be, okay? Use a chain rule, right? It should be half divided by 8t squared plus 9t to the fourth power. Then I differentiate the inside. It's a 6t plus this, okay? Okay. Yeah. And then you simplify a little bit. So that will be 8t plus 18t cubed. And then here 8t squared plus 9t to the fourth power. Okay, based on the information I have here, I do need to find the curvature, okay? So remember, the curvature is going to be r prime times r double prime, and divide by this cube, right? So I have to find the cross product of those two. Okay?
Shouldn't the top also be the magnitude?
No magnitude. The top is magnitude. Yes, that's right. So, but if you look at the formula I have here, the normal component is going to be k times lambda squared. So the normal component is going to be k times lambda d squared. But this is a lambda already in the denominator, right? So actually, you only have, you just need to define by, divided by the magnitude. Yeah, you call
Could you scroll up because we can't see because of that? Yeah, thank you.
Okay. All right, so I needed to find the cross product. Okay, how to do that? So ijk. Okay, I remember the first derivative 2t, 3t squared. Then second derivative 2 just differentiate again. So when you when you do the computation, you will get, and this part of the first component, 2 times 6. Okay. Yeah. So this part, this matrix, right? 2 times 6 is 12 t squared minus 6t squared. So it's I minus. Then have a 12t squared minus 6t squared. That's j. And this part will be 0, I think. Yeah, 4t minus 4tk. Okay. So this part is 0. What I get is 6t squared I minus 6t squared j. All right, so that's it. You know, I can calculate the curvature, but I just want to find a component. And then I just need to plug them into the formula as a length. Okay, it's going to be, yeah, we always say the norm of the vector, not the magnitude. Sorry. Okay, it's going to be 6t squared and squared plus negative 6t squared squared. And what is the denominator? The norm of this vector, right? So it's going to be 8t squared plus 9t to the 4th power. Okay. So we simplify it, and that is going to be 6 squared root 2 t squared. Now, if you assume t is positive, you can simplify it further. Okay. Otherwise, just leave like that. If t could be negative, so you have to keep the absolute value of t if you take t squared out of the radical.